thanks for the invitation to speak at this great workshop. And apologies to anyone who's sort of heard this talk before, but I know Eyal's given quite a few talks about this, and so I'm going to try and talk a bit more about, or less about our sort of first application of this theory, which is showing cutoff for the Ising model, and more about the way in which we can use it to understand the effect of different initial conditions. So I'm going to be writing on the board. If this is if you're sitting at the back and this is too small, then I'd suggest moving further to the front. But if you have brilliant eyesight, then that's great. And if I start to write too small, let me know. Okay, so I'm going to be talking about sort of a dynamics for the Ising model. Now, probably quite a few of you have seen the Ising model before, but I'll just describe it to begin with. It's a model of a sort of ferromagnetic system, so it comes from statistical physics. I guess originally it's meant to be modeling sort of the magnetics of a piece of iron. And so you have a graph. And for the purposes of today's talk, we'll usually think of the graph as being a piece of the lattice, ZD. Either just a piece with sort of cut out with free boundary conditions, or maybe with periodic boundaries. So really a torus if we want it to be transitive, because that can be that's not necessarily essential, but it can make some of the arguments easier. So it's a probability distribution over configurations which assign pluses and minuses to each of the vertices. So a configuration might look like this. And sigma, which we'll use to represent a configuration, will sort of be just assignments of pluses and minuses to each vertex. And the distribution over the configurations will be according to this Hamiltonian. So it's beta, the inverse temperature, which is the main parameter of the model, times the sum of sigma u, sigma v, where we're summing that over all pairs of vertices in the graph. So what this does is, you get a 1 here if sigma u and sigma v are the same, and you get a -1 if they're different. So the probability distribution will tend to put more weight on configurations where you have more pluses next to pluses and minuses next to minuses. The spins, and I'll call the pluses and minuses spins, tend to want to align. And the strength of those interactions are governed by this parameter beta. Okay, and this has been, there are probably thousands of papers about the Ising model. It's one of the most sort of highly studied models out there. And it's sort of like the canonical, simple example of a spin system or a Markov random field. Now, when d equals 1, so it's just on a line, things are very simple, because essentially the stationary distribution, if you look at this, it's just a two-state Markov chain. So, that's about the simplest Markov chain you could want to understand, and so the spins will have exponential decay of correlation for any value of beta, and that's what Ising originally proved. Unfortunately, he thought the same thing also happened in the case of d greater than or equal to 2, but there you get sort of a different behavior. So if we look at ZD when d is greater than or equal to 2, we get there's a critical value of beta where two different things happen. When beta is small, these interactions are very weak. And so if you look at two spins a long way away from each other, they'll tend to be sort of very weakly correlated. And actually the covariance of sigma u and sigma v will decay exponentially in the distance when beta is less than beta c. But when beta is greater than beta c, you won't have decay of correlation. The correlations will be sort of strictly bounded below, and the reason for this is when beta is, so this is when beta is greater than beta c, and the reason for this is when beta is very large, the best configurations will be ones that are either mainly pluses with a few small islands of minuses, or mainly minuses with a few small islands of pluses around. And so the configuration will make a global choice to be either mainly plus or mainly minus. So even very far away vertices will be correlated. So this is a Markov Chains mixing time workshop. So we'll be looking at I should say, sorry, before I go on to that, at beta c you get actually some of the most beautiful mathematics. So in D equals 2, Smirnov and his collaborators proved convergence of interfaces between the pluses of minus to SLE and sort of conformal invariance, and that was one of the main parts of his sort of getting a Fields Medal. We're going to be focusing on the case where beta is smaller than beta c for this talk, so where the decay of correlations is large. Okay, so you have a fairly canonical spin system. You can ask, how do you sample from the distribution? And there are several algorithms, but the simplest one is to do the sort of heat bath or Glauber dynamics, which is as follows. And I'll talk about the continuous time version of it. So for each vertex, there'll be a rate 1 exponential clock. And so when the clock rings, let's say on this vertex, we'll update the spin. So we'll delete its current value, and then calculate the conditional distribution given the rest of the configuration. But you can see from the distribution here that it's only going to matter. It's only going to depend on the neighboring values of the spins, and actually the conditional probability that it's a minus given its neighbors is a half 1 minus tanh of beta times the sum of the spins there. That's just a sort of basic conditional probability calculation you can do. So we could do this update by saying, okay, we'll take a uniform random variable between 0 and 1, update it to minus if u is less than or equal to this conditional probability, and plus otherwise. So we look at the neighbors and calculate the conditional probability and update it to a new value according to those. And we do that for each vertex at rate 1. So in 1 unit of time, we'll do on average about n updates if there are n vertices in the graph. Okay, so that's the dynamics. And we can ask, okay, how does the mixing time of this dynamics depend on the temperature and depend on the size of the graph? So if by now you haven't, I'm not going to define the mixing time. If you haven't learned it by now, then shame on you. It's been in about 6 different talks so far. So this was, the main work of this was done in the 90s, particularly by Fabio and various collaborators, and showed that when beta was less than, so let's say that this is on the torus, Z in Z over nz to the power of d. When beta is less than beta c, the mixing time will be logarithmic, whereas this is all these. There are constants in all of these, but it will mix very quickly when beta is less than beta c. You'll get a logarithmic bound. But when beta is greater than beta c, it will become exponentially slow in n. And the reason for the slow mixing here is essentially because of the way the configurations are either predominantly plus or predominantly minus. There's a bottleneck going between those two states, and it takes exponentially long to pass through them. Okay. Actually, at beta c is sort of a question mark still. We expect it to look like some polynomial. In 2 dimensions, we have upper and lower bounds, which are polynomial, but we don't know that there's sort of some actual exponent here. In higher dimensions, we don't even have I don't know. We certainly don't have a polynomial upper bound, and we probably don't have a sub-exponential one, at least in high dimensions. Is that fair, Fabio? Or, yeah. Okay, so this is a very interesting sort of understanding. This would be sort of a very interesting topic that we don't understand that so well. Okay, so our focus will be in the high temperature regime, understanding. So we know that it's logarithmic. We want to understand first the fact that this has cutoff, and secondly, understanding. So this is for the worst case mixing time, how it's affected by taking sort of different initial conditions. Okay. So previously sorry, I should have said at the beginning, this is all, what I'll be talking about is all joint work with E.R. Lubetsky. And maybe about 5 years ago now, we showed that when d equals 2, when beta is less than beta c, you have cutoff. Sort of about 09. Cutoff when beta is less than beta c, and d equals 2. We wouldn't expect cutoff in either the critical or the high temperature regimes, I think. But for larger values of d, we could only prove cutoff for a more restricted value range of beta. And the reason for that is this proof used in sort of an essential way that we have a bound on the log Sobolev constant in the high temperature regime. And this is a result of Fabio in 2 dimensions, but we don't know it all the way up to the critical temperature in higher dimensions. But so today's results, which is from earlier this year, is that first of all, we have cutoff for all d greater than or equal to, actually for all d, when beta is less than beta c. In 1 dimension, actually, this is cutoff for all values of beta, because there's no phase transition. We already knew that before. we prove that the window is sort of a constant width. Before, we had something suboptimal that it was log n. And our results also extend to other graphs as well. So on a general graph, we have cutoff if beta is less than or equal to some epsilon over d, where d is the maximum degree. So as long as beta is sufficiently small as a function of the largest degree of the graph, then you have cutoff on any sort of growing sequence of graphs. Okay. So, yeah. Yeah, so I guess in this regime you would have pre-cutoff. Essentially, you can show that the monotone coupling sort of mixes with, couples with high probability at a value that's essentially twice the mixing time. So, yeah, so essentially, this was this was out by a factor of 2 in a sense, I guess. Yeah. Okay. So the way we're going to study it is to give a sort of more geometric picture of the way in which the dynamics mixes. So you can imagine we have a series of updates at different times, and each of these have a unit variable associated with them, and so on. So this says that so if the x-axis is sort of the graph and the y-axis is time, then this is saying that at vertex v at time t prime is getting an update here. So what that means is you forget the spin at this vertex, and then apply this rule and update it to either plus or minus, depending on the values of the neighboring vertices and what unit random variable we chose. So this gives us a way of constructing a coupling which takes the initial configuration and gives us the final configuration at time t. So that's so this is what you might call a grand coupling. So you take all possible initial configurations at the beginning, and if I tell you what the updates are, I can tell you what the final configuration is as a function of the updates and what you began with. Okay. So what I want to study is, I have a vertex v here, sort of the history of what spins you need to know in order to calculate sigma vt. So I'll write that the history of v and t at time t prime less than t is the smallest set of sigma, or the smallest set of, let's say, S, a subset of all of the spins, such that you can determine sigma v of t from sigma v prime of t prime for v prime in S. So what does that mean? Well, suppose that v was never updated. This means that its value just never changes. So then the history of v would just always be v. You can work out the value here because it will always just be the same as the value at t prime. So if there are no updates, the history will just be a straight line going down from there. On the other hand, suppose we had another vertex, and at some intermediate time, it got updated. So then, in order to work out what the spin is here, we need to know the update here, plus the spin at these neighboring vertices. And for a time further back in time, we'd need to know the history of these ones. But now perhaps these also get updated, and we'd have to know their history, and these could merge together. And eventually we might need to know more and more vertices in order, the spins of more and more vertices to be able to work out what the spin was up here. So we want to understand the geometry of this sort of set of dependencies. So which vertices do you need to know at time t prime in order to get to calculate the value at time t? And it may at first look like this is just going to explode and will require more and more information as time goes on. But actually, when beta is small, this will turn out to be very subcritical instead, and we'll need to know less and less. And so let's define an oblivious update. If U is not an element, so if U is not in this window, what does that mean? Well, let's look at the rule for defining it. The smallest possible value that this could take is a half minus a half tanh of beta. So if U is less than that, we'll always set it to a minus. And similarly, the upper bound of the interval is such that if U is bigger than that, we'll always set it to a plus. So when U is outside of this interval, when it's oblivious, it can just set the spin independently of the neighboring values. So when we have an oblivious update, we can just sort of kill this line of descent. And so maybe these ones also die out. And so it's possible for these histories to just be completely extinguished. At that point, the value at time t depends only on the updates. It doesn't depend at all on the initial configuration. And now when beta is really small, the probability of having a non-oblivious update is hyperbolic tanh of beta times d. So when beta times d is small enough, that probability will be really small. So that will make this sort of kind of branching process-like object, this history, extremely subcritical. And so its size will tend to decay at an exponential rate, like a subcritical branching process. And you can sort of stochastically dominate it by like a continuous time subcritical branching process. So in this regime, if we looked at all the histories, a lot of them will just die out without doing anything. Some may go a bit further. They may sort of run into each other as well. But if we have a long enough period of time, they'll all just die out before reaching time zero. And what does this correspond in terms of, sort of the usual approach to mixing times? This is exactly the point. If they've all died out, that's exactly equivalent to the monotone coupling, having coupled the all plus and the all minus conditions. So definitely we know that when all of these sort of die and don't reach the bottom, then, if that happens with high probability, then it must be mixed. And the time at which that happens is going to be, let's assume that this is a transitive graph just to make things easier. And I'll say the magnetization is the expected spin of a vertex starting from the all plus condition. Then the point at which, first of all, this is going to decay exponentially in time. The point at which things couple will be the point at which mt times n is equal to 1, or the magnetization of the vertex is about 1 on n. Okay, but this is going to give us, this is actually going to give us twice the mixing time. And the reason for that is, suppose one or two of these histories actually did manage to reach the bottom. Then for these vertices, their spins will depend on the initial configuration a bit. Well, I mean, a lot actually. They'll be different if they're all plus versus all minus. Okay, but when you're deciding whether the configuration at time t is mixed, you don't get to see all these histories. You just see the configuration itself. So we don't know which of these ones were affected by the initial condition or not. We just see whatever the configuration is. So the sort of picture you can try and imagine is that when we have a few rare histories, they change the distribution a little bit, but mostly they're just lost in the noise. There's a lot of, the vast majority of spins will not be affected by the initial condition, and these ones will. Okay. Yeah.
So this probability window you put up here seems to depend on the dimension.
Oh.
Do you believe that also the cutoff you would only be able to, you would have to choose beta pretty small?
Yeah, well, yeah. Actually, this d was supposed to be the maximum degree rather than the dimension, but your point is quite right. So first of all, the beta c does depend on the dimension, and actually it does scale like sort of 1 over the dimension. So yeah. So actually you can show that if certainly if beta is greater than 1 over d. Okay, maybe a little bit. What is it? If d minus 1 times hyperbolic tanh of beta is greater than 1, then you can have exponentially slow mixing. And when beta is small, when d is large, this corresponds to roughly beta about equal to 1 on d minus 1. So 1 over d is really the sort of right sort of trade-off between beta and d. So if you take, if you take a random deregular graph, then if you have d minus 1 tanh of beta is greater than 1, then the mixing time is exponential in the size of the graph. And this is sharp. If it's less than 1, then the mixing time is logarithmic. So, and this value corresponds to the sort of where you have a phase transition, not on a lattice, but on the deregular tree. But yeah, so our results will depend on D. The way I'm going to tell the proof will actually get a much worse dependence on D than we get in the paper, because to get sort of constant over D rates, there are a lot of extra things that you need to do to kind of get better estimates. And I'm going to sweep that all under the carpet. So, okay, but yeah, good question. Any more questions at this point? Okay. So so actually, the point at which, if I define T star as sort of the solution to MT star equals 1 on root n, then it will turn out that T mix is equal to T star plus sort of a constant term. So the point at which the magnetization becomes 1 over square root of n rather than 1 over n will be the right mixing time. So MT decay is it's really like an exponential. So you can see that this is really twice. This sort of coupling time really corresponds to twice the mixing time here. Okay, so first let's just see that this is a sort of plausible value by doing a lower bound. And we can do that by looking at sort of a test function, which just involves, say, the sum of the spins times the magnetization. If we wanted to do this on a general graph, actually, you'd replace the magnetization here with the magnetization for the particular vertex. So the expected value of y starting from all pluses will just be equal to sum of mt squared, or n times mt squared. The expected value starting from the stationary distribution of y will be equal to 0 just by symmetry. And the variance of y, actually under either of these initial conditions, is also equal to, well, it's not equal, but sort of asymptotically n times mt squared. And the reason for this is, I told you that when beta is small, you get sort of good decay of correlation. So if you calculated the variance of this, assuming that they were sort of weakly enough correlated that you could just add up the variances of individual terms, this is what you'd get. So the variance is the same order as the difference of the means, but that means that if n mt squared is big, then the difference of the means is much bigger than the standard deviation of this random variable y. So so if you look at the set of sigma such that y of sigma is greater than half n mt squared, this will give you a sort of good test statistic for comparing the stationary distribution with the all plus initial condition. And we'll get the sort of T mix is you can show using the fact that MT decays exponentially that it's T star minus so if we go sort of log of 1 minus epsilon less, then we get Tmx of 1 minus epsilon as a lower bound. Okay, and we want to show that we get sort of the opposite bound, that Tmx of epsilon is less than or equal to T star plus C log 1 over epsilon. Okay, and it will be this that will need this sort of new machinery in order to tackle. Okay, any questions? Okay. So now I want to look at the histories, but in a sort of color-coded way. So what the colors are meant to indicate is, well, we'll split the histories up into 3 groups. Oh, well, first of all, actually, some of the times the histories will run into each other. And maybe it does this as well, actually. And we'll group together ones into components where they run into each other. So if here the history of these 2 vertices intersected. And we'll color these components, first of all, red, if they survive to the bottom. So if they hit the bottom, these are the ones that can be affected by the initial configuration. We'll color them blue if they're just a singleton, so they don't reach the bottom, and they don't intersect any of the histories of any of the other ones. And finally, green otherwise. So, well, some basic observations. The red ones, most vertices aren't going to reach the bottom, so the red ones will be very rare. The majority of vertices are going to be blue. They just sort of die quickly and not intersect with any of the other ones. But the blue ones, if by symmetry they're sort of equally likely to be plus and minus, and their spins, the spins at each of the blue vertices, are completely independent of each other. So on the blue vertices, we just get a nice field of IID plus minus random variables. And then on the green ones, these are ones where the histories intersect. Now the vertices in the same green component might have some complicated joint distribution. This is essentially where all of the structure of the Ising model is going to take place. So the green ones are sort of the most complicated, and so we're going to basically ignore them. And the way we're going to ignore them is by doing everything where we condition on all of the green components. And so we're just going to focus, so we'll condition on the green ones and then focus on the red and blue ones. So that was a picture of the history. Let's draw what this looks like on the graph. So we'll have some regions which are green. This will be a a constant fraction of the graph. We'll have now just an occasional very small red component here and there, and everything else is going to be blue. So it looks like sort of an IID field of plus and minuses. So once you condition on the greens, on the complement of the greens, it looks like an IID field of plus and minuses, plus these occasional vertices which are affected by the initial conditions. Okay. And the tool we're going to use to, take advantage of this structure is a lemma by Yuval and Jason Miller, which they used to analyze cutoff for the lamplighter walk. And they showed that, okay, suppose we construct a measure mu on configurations on a graph as follows. We choose some random set R, which will be a subset of the vertices, and and we put IID plus minuses on the complement of R and set the spins of R sort of arbitrarily. So we have some set R. We can set which is randomly chosen. We set that however however you like, any random or deterministic rule you want. And on the complement of R, you just set everything independently as pluses and minuses. And so the question is, can you distinguish this from just a fully IID sort of set of pluses and minuses? And the result they came up with was that if you look at the L2 measure between mu and nu, where this is sort of just the IID measure squared, is less than or equal to the expected value of 2 to the R intersect R prime minus 1, where R intersect R prime just mean where R and R prime are two independent copies chosen from this distribution on sets R. So what it's saying is that if R isn't too big, and if it's not in the same place too much of the time, then you can get a bound on this and get a bound on the L2 distance. So translating this result into our setting, we condition on the full history of all the green ones. And we get the total variation distance from, say, at time t, from two different initial configurations. Given, so where h of g is going to be the history of the g ones. So we take the conditional expectation of r intersect 2 to the r intersect r prime, where this is just, where r in our case will just be the set of the reds. They're the ones that aren't IID, that can be determined by the initial condition. And this gives us, and so this is the bound that we then work with. So we can reduce the problem of understanding the mixing time to the problem of understanding essentially the geometry of these red components, the ones that are affected by the initial conditions. And then we need to take advantage of the fact that when beta is small, these are very subcritical. And because they're subcritical, we can get a bound along the lines of the probability that a set A is red divided by the probability that it's sort of all blue, conditional on the history of everything outside of A, is less than or equal to a constant times the magnetization. This is sort of the chance of something being red, times e to the minus, let's say, 100d times some measure of the size of A. So we could take something like the size of the smallest spanning tree or the smallest lattice animal that includes A. So we want to ultimately we want to enumerate over A, and so we want to penalize sort of components that sort of look something like this, where the set involves far apart vertices. So this is real, but this is really like a percolation sort of estimate. And you might worry that conditioning on the history of the green ones might make things terribly complicated. And it does make things a bit complicated, but what does it mean to condition on the greens? Well, it means that a given set has to either be red or blue, first of all. So comparing this ratio is sort of the right thing to do there. And it means that the components just can't intersect the green ones. So those are both things that you can work with. And this is sort of a percolation / branching process estimate that if you think about for a while, you can prove. And because we can get sort of good enough decay on the probability of seeing a large set A, most of the contribution to this term is just going to come from when we have two reds that are just singletons, just components by themselves. And in that case, the probability of a vertex being both in red and red prime would be like the magnetization squared. So very roughly, we'd get the is expected value of 2 to the binomial n mt squared, which is roughly 1 plus mt squared, or order of mt squared, as long as mt squared is less than or equal to 1 on n. So it's really, it boils down to something which is really just like 2 to a binomial. And then from here, the exponential decay of mt will do the job for us. Okay, any questions about that? And you can do this bound. So I mean, this should be conditional on the history of the greens, but you can get this bound sort of uniformly for any history of the greens. Okay. So using that, we can sort of pretty efficiently analyze the sort of the worst case mixing time. But using this structure, we can analyze other mixing times as well. So if you were trying to get your Markov chain to mix faster, if you were using it as an algorithm, you might say, well, I don't want to start from starting from the worst possible initial configuration is sort of choosing the worst possible algorithm of this sort. We'd rather start from the best possible initial configuration. So one thing you might try and do is look at sort of an initial configuration x0, which is chosen sort of from nu, the IID measure. But it turns out that this is not going to increase or decrease the mixing time by much. So if we're on this is on a lattice, if we look at the mixing time started from x0, then this will be greater than or equal to the worst case mixing time minus a constant times log n. So remember, the worst case mixing time is order log n. So this only improves it by sort of a logarithmic factor. So, it doesn't get much better. Oh, and I should say the probability of this tends to 1. We might expect, and let me give you the reason for that. We'd like a test function a bit like this one, where we look at the magnetization, the sort of sum of the spins. But now we should look at the sum of the sigma vt times the expected value starting from x0 of sigma vt. So we should weight these by their expected value. And then, so we call this y. Again, the expected value of y starting from the stationary distribution will be 0. The expected value of starting from x0 will be sum over v x0 sigma vt, sum of the squares of these sort of magnetizations. And so now we should just ask, how big should these magnetizations typically be? Well, the value here is only going to be affected if its history reaches down to the bottom. And typically, if it reaches down to the bottom, a lot of the time it's just going to reach the bottom at a single point. And so then if this point is plus or minus, then that will make this one plus or minus. Now, so the probability of it coming down and hitting a particular vertex is roughly like, well, these are only going to travel a logarithmic distance, so it should be roughly like mt over something logarithmic in n. So this would be the effect on the magnetization here of changing this vertex from, say, a minus to a plus. You get a variation of about this much. So the typical order of this expectation should be at least as much as this. And so we should expect this to be bigger than mt squared over, again, something logarithmic. Yes? Why is this expectation? This is the expectation starting from sort of x0. So from a particular, yes, yeah, no. So this is the quench setting. So where we take a particular x0 and look at the mixing time from there. Yeah, no, that's good to clarify. Okay. And so we're going to, this lower bound is going to give us a lower bound on the mixing time when this value is sort of significantly bigger than 1 by the same argument that we had for the worst case one. And this will be essentially exactly the same time as the mixing time, except minus a log-log factor. And you need to do some concentration estimates to get this probability, but essentially that's the way it goes. So in the quench setting, you don't get much improvement at all by taking a sort of random initial configuration. But if you're trying to sample from the distribution, you wouldn't do that. You wouldn't just sort of take a fixed initial. You wouldn't measure things by saying, how bad does it look from some randomly chosen one? You would set the initial, you'd set the Markov chain such that its initial distribution was sort of IID pluses and minuses. And let's do this in the case of Z1, just on the line, because it's simpler. So in this case, what we get is that T mix of nu is essentially half the worst case mixing time. So by taking an annealed started configuration, the Markov chain mixes twice as fast. And yeah, so my initial sigma naught is just taking IID pluses and minuses. Yes. Yeah, exactly. So now we have these red components. Okay. If we look at a single red component, and we either have pi or nu as our initial configuration, for each of them, the value down here will be equally likely to be plus or minus. So the spins we get on a single component are going to be, will have the same distribution under both of these initial configurations. But the joint distribution of them will be different because the values, if you start from the stationary distribution, you get a correlation down here. So the way in which we can handle that is by simulating an initial distribution of pi by sort of continuing the history back to minus infinity and seeing what these histories do after that. And this is nothing but Propp and Wilson's sort of famous coupling from the past argument. And so if you start from time minus infinity rather than time 0, this will give you exactly the stationary distribution both at time 0 and at time t. And we can compare what happens to the components when we do that versus when we put IID spins here. And we'll get the same distribution on the components unless they merge below time 0. So really we should define anything that doesn't merge before time 0 as being, say, green. And the new red means sort of it has a merging below 0. And for this to happen, two close by strands have to make it down to time 0. So the chance of that is mt squared. And so when we'd calculate the probability of having a new red variable, we'd get an extra square here. And the mixing time will correspond to the point at which n mt to the fourth is equal to 1. And this is half the mixing time before. So and I have about a minute left. So I just want to summarize for different initial configurations. So this is at d equals 1. So yes. So Yeah, that's a good question. So the lower bound you would get by looking the lower bound. Yeah, you can get by looking at the Hamiltonian, the value of the Hamiltonian. So sigma u plus 1. And roughly, so if you have two consecutive vertices, we roughly want to know what's the chance that they're the same is exactly the chance that they're in the same component in one dimension, and that's and we'll get a difference there in whether or not they're same between these two initial configurations, exactly depending on whether or not they merge before time 0 or after time 0. So if you look at this, if you look at the Hamiltonian of sort of the, then that gives you a test statistic for a lower bound, which exactly matches this one, or at least up to lower order terms. So if we look at the mixing time, for the worst case, we get log n on 2, 1 minus tangent beta. For the quenched, we get the same thing minus log n. For the annealed, we get half of that. Well, so these are two sort of random initial configurations you could take. Just to end with, what would you suggest for a good sort of deterministic initial condition? Any guesses? So you want one that's sort of balanced between pluses and minuses. So a good one to take is plus minus, plus minus, plus minus. And what you get for this one is it actually is the formula has a phase transition. You get log n times the maximum of 1 on 2, 1 plus tangent beta, and the annealed one, 1 on 4, 1 minus tangent beta. So if you look at the graph of the mixing times, this would be the worst case. This would be the annealed case. The quenched is essentially the same as the worst case, and the plus minus one would look something like this. It would it actually gets better for a while as the temperature, as beta increases, and then it gets worse and follows the plus minus initial configuration. And we analyze this as well using the same sort of technology. And I'm out of time. So, thanks.